Welcome to this lesson on repetition structures, also known as loops. After reviewing this lesson, you should be able to differentiate between a looping condition and a loop exit condition, differentiate between a pretest loop and a posttest loop, include pretest and posttest loops in pseudocode and in a flowchart, write a do loop statement, and utilize counters and accumulators. Let's explore the structure of a loop. A loop is fundamentally composed of two pieces. There is a test, which is used to decide whether to run the logic of the loop body or to exit the loop, and there is the loop body itself, which is the set of instructions that are repeated each time the loop iterates. There are a couple different ways we can categorize loops. Some loop structures have the loop test up front before the loop body. These are known as pretest loops. Other loop structures have the loop test following the loop body, posttest loops. In general, these structures do the same thing. However, there is an important difference in terms of how many times, or the minimum number of times, that the loop body will execute. Because the loop body is executed before the test in a post-test loop will always execute the logic, the code contained within the loop body at least once before the loop is evaluated and may or may not repeat. In a pretest loop, if the test is not satisfied, the loop body may be run 0 times. It may never be run, may be skipped entirely. Why do we need both types? Well, frankly, some programming or logic situations lend themselves more to one situation than the other. So having both structures allows us to use the code structure that most naturally fits the situation we are coding. And the code clarity is much greater when you are addressing a problem and can express it in the programming language with a logic structure that sort of naturally fits the situation. We'll see that more in upcoming examples. Let's explore an example of a post-test loop. So in a post-test loop, the actions of the loop body are always going to be run first before the test is executed to determine if additional iterations of the loop are to be run. Okay, so we're always going to go ahead and do one. So the minimum number of times the loop body will run in a post-test loop is 1, as compared to a pre-test loop, which if the test isn't met, since the test happens up front, you might run the loop body 0 times. You might not run it at all. So here's an example where a post-test loop kind of makes sense. So we've got boardwalk carousel. It's a carousel on the boardwalk, and everybody that's in line for tickets, our assumption is they're going to buy at least one ticket. Otherwise, what are they doing in line? Don't bother me, kid. Go away. You're wasting my time, right? So we're going to assume that everybody in line at the boardwalk carousel is going to buy one ticket, and then they may or may not buy additional tickets. So we'll use a post-test loop to charge them for their first ticket by virtue of the fact that they're standing in line. And then, you want another ticket, you want another ticket, you want another ticket. As long as they keep saying yes, you just hit the ticket sale button and it rings it up. And just for fun, we've made the first ticket cost $2, and every additional ticket will be $1.50. So here's how that works. We're going to go through our housekeeping and do some declarations. So I'm going to keep a integer counter of the number of tickets, and we'll initialize that to 0 before we use it. And then let's have a real valued number of the total due, and that's going to be where we store the current amount of the total due, and it will be updated every time the loop adds another ticket. And then we need a string to store the user's response. Do you want more tickets? Do you want more tickets? And if they give us an affirmative, a yes, so capital Y or lowercase y in the input, then we will add more tickets. And if they give us anything else, we'll just assume that they meant no, and we'll ring out their total. Okay, so the program opens, we give them a nice welcoming message, welcome to Boardwalk Carousel, and then we can automatically tell them your first ticket is $2, additional tickets are only $1.50 each, and now we enter the loop. Now notice that we're going to execute the loop right away without testing it. We don't test it till the end. So immediately we're going to take numticks, which was the number of tickets which was originally 0. We're just going to add 1 to whatever that number was the first time through. It'll be 0. So now we're buying 1. Our formula for the total due is to take $2 and add that to the one less than the number of tickets times $1.50, and that's because that first ticket, this is the first ticket at $2. Every additional ticket is going to be $1.50, so the number of tickets at $1.50 is 1 less than the total number of tickets. So that's a little trick in the formula there, and then we'll go ahead and give them their message. Output is you have purchased, concatenate with number of tickets, and your total due is $ concatenate with total due. Then we prompt them, do you want to buy more tickets? That's our output. And then we get their input, which should be either uppercase Y or lowercase y based on the prompt we gave them. We're not doing a lot of error checking on that. That would probably be better if we were writing a real professional program, but we're going to just keep it simple for demonstration purposes. So the user enters a yes or a no, Y or an N. And so if buy more has the content of a uppercase Y or buy more has a lowercase y, then the loop is true and it will repeat. If it's anything else, it will fall out. The ticket taker hands them the tickets after taking their money and says, enjoy the carousel. So let's go ahead and run that and see how that's gonna work here. So we run that. Welcome to Boardwalk Carousel. Your first ticket is $2. Additional tickets are only $1.50 each. You have purchased 1 ticket so far. Your total is $2. Do you want more tickets? And this is not a counted loop. We don't know in advance how many they'll buy. So this is also an indefinite loop as well as being a post-test loop. And let's say, yes, I want another one. And it says, great, you have purchased 2 tickets. Your total is $3.50. And is that right? $2 for the first ticket, $1.50. Yeah, so $3.50 is right. Do you want to buy more tickets? Yeah, sell me another ticket. Sell me another ticket. Sell me another ticket. Sell me another ticket. Okay. So now I've purchased 6 tickets. I owe them $9.50. I've only got $10 on me, so no, I don't want to buy more tickets. And it says enjoy the carousel. So that's how our loop works there. And again, the point here is that it is a post-test loop. We're running the loop body. So here is our loop body. We're going to run that at least 1 time to sell them their first ticket, and we'll only run it additional times if it matches the or passes the test that they want more tickets, and we'll continue to loop through every time they want more tickets. And when they no longer want more tickets, then we exit and the program will end. Pretty simple stuff. A couple technical terms here. So we're taking and adding to a total each time we go through. The total due is updated. So that is technically an accumulator. Okay. And then we are exiting. Our exit condition is on uppercase Y or lowercase y. So that is known as the Sentinel value. It stands Sentinel, like a sentry, asking for passwords, looking for when the condition is met. If the condition is met, you know the password. We run the loop again. If you don't give me the right password, then we drop you out and you end the loop. That's it. Now let's explore a pretest loop example. So in this scenario, the boardwalk, maybe for economies, maybe they've had a downturn in business, but they've consolidated their information kiosk and their ticket booth kiosk into one booth. And so some of the people that are coming in line will want carousel tickets, but some just have a question or want directions. Therefore, we're going to test to see if the customer wants any tickets before we set up a charge for that customer, okay? Because it's possible that they don't want any tickets. The loop body won't run even once. It'll run 0 times, okay? So as usual, we start with our housekeeping. We declare the number of tickets. That's an integer. Declare that as 0 to start with. set up a real total due, and again, we'll assign that before we reference it coming up here. Same for string buy more, and unchanged from our last version was welcome to Boardwalk Carousel. But now it's going to ask, do you want to buy carousel tickets? Because they may just be here for information. Okay, we're really only interested in the yes answer. Our program's not going to handle the no answer. Presumably the person behind the kiosk is going to answer their questions if they have questions and don't want to buy tickets. So get the input. Do they want to buy more tickets? Because any is more than 0. So yes, and so if they answer yes, then we're going to execute our loop body because they will have passed that test. If they answer no, so negative on that test, then this loop body will not run even once. It'll run 0 times, and it just goes. We've changed our exit message to enjoy the boardwalk, because some of the people that will have completed the program may have bought tickets and others may not, but we'll just wish them a happy time on the boardwalk instead of specifically on the carousel. Okay, so if they do buy tickets, then we've added, or we've relocated our message about the pricing of tickets in here, and so it'll be a little redundant each time it goes through the loop. It says your first ticket is $2, additional tickets are only $1.50 each. Since we've already affirmatively said we're buying tickets, we add 1 to the number of tickets. We recalculate and display, you bought this many tickets and your total is now this. Do you want to buy more? And now we're back into the loop for additional iterations. As long as they enter an upper or lowercase y, then their ticket total will keep climbing. And once they enter something other than that, presumably a no, an N, then it'll exit and give us output, enjoy the boardwalk. So let's actually see this in operation. All right, so welcome to Boardwalk Carousel. Would you like to purchase carousel tickets? No, I just have a question. And so presumably the cashier answers my question, and where are the restrooms? Where can I buy cotton candy? Who do I complain to about the quality of your funnel cakes? Whatever, and then without it running the loop for buying tickets, just says, "Oh, enjoy the boardwalk." Okay, so we can run through that program without ever executing the loop at all because it is a pre-test loop. Okay. Let's try it again. And do you want to buy tickets? Yeah, sure. I want to go on the carousel. Do you want more tickets? Yeah, I've got a kid. Oh yeah, probably also ought to take care of my kid's best friend who's with us today. Oh, did I say no? I did say no. Ah, silly me. Let's run it again. Okay. Yes, I'd like to buy tickets. And do you want to buy more tickets? So I have $2. Yeah, I need one for my kid. And you're now owing $3.50. You've got 2 tickets. You want more tickets? Oh yeah, my kid's friend is with us today. I better buy a ticket for my kid's friend. And yes. And do you want any more? It's like, no, I'm just gonna sit and watch while my wife and my 2 kids, or the kid and his friend, go on the carousel. So 3 is all I need. I'll say no, and it's back to enjoy the boardwalk, and the program ends. And just again, to revisit what we've learned here, this is, see the position of the test, which occurs before the loop body, making this a pre-test loop structurally. Numticks is accumulating the number of tickets purchased, and then we're calculating the total on our formula. And then the Sentinel value is it's looking for a y, capital Y or lowercase y, to continue. A Sentinel value is a match anytime it is not that. So the negative it meets the exit condition, and then we just go out and say enjoy the boardwalk. And again, to sum up, being a pre-test loop, it is possible to not satisfy the test on the very first try, which means that the loop body will never be executed. So the minimum number of times the loop body on a pre-test loop can run is 0. The maximum of course, this is an indefinite loop rather than a counted loop. So theoretically, you could sit there saying yes forever. Um, and so we probably ought to have some limit in rationality and shut the customer down once they get past some ridiculous number of tickets. It's like, hey, we can't accommodate more than 1,000 people in a day. Why are you buying 2,000 tickets? Um, we'll leave the ridiculous cases for later discussion and data validation. We've seen how loops can be categorized as pretest and post-test loops. A second way to categorize loops is as definite versus indefinite loops, or another way of expressing this is as counted loops versus conditional loops. In a counted loop, the number of times the loop needs to repeat is known prior to the execution of the loop. Now that doesn't mean we have to know at design time when we're building our code exactly how many times that a loop will repeat. For example, we may repeat the loop a given number of times based on a user input. So it isn't necessary to know that in advance at design time. We can find out at runtime. However, we do have to know definitively a set value of how many times a counted loop will run before the loop begins to run. Alternatively, we can have an indefinite loop. And an indefinite loop, as the name implies, can run an indefinite number of times. The cause of the loop's ceasing is going to be dependent on some event that is encountered in the data that's being processed or some input that is garnered during the loop's body's execution. So we might ask a user during a loop, do you want to do this again? Do you want to do this again? Do you want to do this again? As long as the user keeps saying yes, then we would repeat until the user is satisfied with the input or satisfied with the results. In the case of instrumentation, we might have a loop that runs until some sensor indicates that a process has completed or a situation has been encountered. So it could be data driven, and the data can be provided either by the user or by an automated process or by a file that's input data that we're processing. We keep going. For example, a very simple example would be we process all the data. So the end of loop condition would be the end of data. So if we've run out of data, then the loop ends and we stop processing. Next, let's explore counted loops, also known as definite loops. So, in a counted loop based on the some value of a counter that is set, it may not be set at design time, it may be set at runtime in response to some user entry or some other value that's acquired through data input or sensor instrumentation, that kind of thing. But before the loop runs, it is known definitely how many times the loop will run. So we don't necessarily have to know at design time, but let's take a simple case where we do know at design time, but it could be determined by user input that simply says, how many times do you want to do this, Mr. User? And the user enters a number. The point being, before the loop executes, we will have set the number of times the loop will execute. So it is not an indefinite loop. It's not a conditional loop. It is a counted loop. And the most common loop structure for that is the for next structure. So we'll put a for in here, and we will need an index variable. So let's declare that going back to mathematical tradition. This kind of came out of when computer science departments grew out of math departments. The variable names for loops that are counted loops, for loops, often we use I or J. It doesn't really matter, any valid variable name. Let's make this an integer, and we'll make it I. Tip of the hat to tradition. And we want to do this loop based on some index variable. So the counter will be I, and we need to give it a start and an end. So this gives us the interval over which the loop will iterate. The interesting thing about this is traditionally you do something like 1 to 10, but we could also have 10 iterations over the interval 0 to 9, or we could do some funky things like -5, actually let's do it this way, -10 to -1. Okay, so we could have the same interval any way you like it. The other thing that's interesting is that we can step in increments of +1. We could also step in increments. We could have a countdown loop, -1. So the start value in this case would be 10, and the end value would be 1. And we could also do some other funky things. Let's make this count to 1 to 20 in steps of 2. And again, if we step by, we need to say increasing or decreasing rather than plus or minus here, I guess is the convention for logarithm. So if we wanted to make this a countdown loop, 10 to 1, step by 1, decreasing, and why the designer did that rather than just having you say step by a negative value or a positive value, I don't know. Might even work with if we did it negative or positive, you know, inverting that decreasing logic. I'll leave that for the student to play around with. But let's go to the simple case that is shown in our lecture slide. So let's go increasing by 1, count from 1 to 10. Okay, so this loop is going to iterate exactly 10 times, and let's show that. And let's say now performing loop iteration number, and we'll concatenate that with I, and do a quick self-test here. What do you expect the output to be, and how many iterations do you expect there to be? Let's test it and see if you're right. Okay. So if we scroll up, we see we started at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so there are exactly 10, 1 to 10 inclusive here. So the other thing that might be interesting to you, or you might be curious about, is you're saying, hey, this is a counted loop, and I can see that I is the index, but we didn't have to put the loop counter in there, the addition of it. So where is the addition happening? Well, that's happening in the way we set up the program structure for this, and said, you know, increasing. What would this actually look like in Visual Basic code? So let's go over to our source code viewer, and let's look at this in terms of our Visual Basic.NET. Actually, let's open our custom template. All right, so let's look at that. And so here's the real heart of it. For I equals 1 to 10, and since it isn't, it's silent on incrementing by 1, that is the default. So it doesn't have to be specifically added if we're incrementing just by 1. And so what is happening is we sort of auto-magically inherit the creamy, delicious golden goodness of the fact that the incrementation between loop iterations is happening. If we were not doing this counted loop using a for structure, and we'll look at that next, we would have to add in to the loop to make it, you know, we'd have to add to I each time through the loop to get it to increment. Okay. So before we abandon this altogether, let's take a look at the countdown loop. So 10 to 1, decreasing by 1, and let's run it again. And so now we're counting down, performing loop iteration 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And there we go. And just for fun, let's decrease it by 2 and then self-test. If we ran 10 times before, when stepping by 1, how many times is this going to run when stepping by 2? Let's test your idea. 10, 8, 6, 4, 2, 1, 2, 3, 4, 5. So that ran 5 times. Okay. And then one final thing that's kind of interesting, because the loop is doing the incrementation of the counterforce automatically when we use a for next structure. Let's turn this back to increasing step by 1, and let's add one other message here. After outputting, actually let's say after exiting the loop, the final value of I was, and concatenate, let's add I onto the end of that message. And what do you think? It's counting down, and something about this for next structure is automatically updating, or in this case, decrementing, or we're counting up. So it's incrementing the counter by 10. So the exit condition for this loop that's implied is when it leaves the range of 10. It looks like I'm still counting up. Yeah. So let's change that from 1, make it a count up loop, to 10. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every time through the loop, it's going to add 1 to it. So the question is, do you think once it reaches 10 and it's ready to exit, well, 10, it must have run on the 10th one, so it's only when it's outside of the range of 10. So does it add 1 more? Well, it must have, so it's when it reaches 11 that the loop is not executed again. So my theory is I, on this, after we exit the loop, should have a final value of 11. Let's see if that's true. And there we are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times the loop ran. But after it exited the loop, what stopped it from running an 11th time was the value was outside of that range 1 to 10, was 11. And so that's an important thing to remember, because after you've used that index, that counter, that I variable, to get to 10, you want to run 10 times, you need to keep in mind that it incremented it 1 more time to get it to exit the loop, and so you don't have 10 stored in there. So if you're going to do more calculations or something based on that, remember that I got incremented 1 additional time, so you may need to decrement it if you're going to use that I value for something else, if you're assuming it's telling you how many times the loop ran, because it's actually saying what was the value when the loop exited, which is 1 greater than the number of times the loop ran. So a little confusing, but as you play with it, it will start to make more sense. All right, so that's one form of counted loop, and for next, it does so much nice stuff for you by taking care of the Sentinel value and the accumulator, that you don't even have to really think too much about controlling the loop structure. There are times when you are going to want a counted loop, but you don't want to use a for next. So let's take a look at that. So let's add instead a while structure. So this will be, I'm using a pretest loop. It could also be done with a post-test loop. That's just a little more awkward for our purposes. And I'm going to cut this out of the first loop and paste it in the second loop. And so can't copy and paste that because while works a little bit differently. So we're really looking for I is less than or equal to 10, right? Now, this initialized I to 1, we're going to need to do that for ourselves. So we're done with this loop. And so here's our integer I declared. Let's assign I equals 1. And now it looks just like our original loop, but remember our for next loop was doing stuff for us automatically, and that's not going to be done for us here. So what do we need to do? Think about it. So let's trace our logic manually. We declare I, we make I 1, we check to see is I less than 10 and 1 is less than 10, and it says now performing loop iteration and prints the number stored in I, which is 1, and it comes back up here, and I is still equal to 1, and it does it again. I is still equal to 1, I is still equal to 1, I is still equal to 1. Oh, so what we need to do is after we've reported on that, we need to increment I for ourselves because a for next loop does it for us. This one does not. So I is equal to I plus 1. Okay, so now it should count through, and let's see if that is true. And we'll also get the bonus of seeing what was our final value after we exit it if we build it this way. Does it still hold true? And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, as before, loop goes to 11. And we can do all the things with a while loop, making it a counted loop that the for next does. So if we wanted to, for instance, make it step by 2, we could say instead of I plus 1, increment it by 2. And so now it should do it 5 times, right? 1, 3, 5, 7, 9. And so that ran 1, 2, 3, 4, 5 times, which we expected, and the final value was 11. Okay. And if we wanted to count down, we'd need to check. We ought to switch a couple things here. We'd switch this and make this the initial value equal to 10. And we'd say, well, I is, in this case, we want to make it greater than or equal to 1. And we're counting down. So I is going to be I minus 1. So there's our count down. So we're updating the counter and running it. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. After exiting, we're 0. And let's see one other trick. So we've been talking about these vocabulary words for loops, and we talked about our Sentinel value, and that's what we're looking for is when I is less than or equal to 1. That's our condition to exit the loop. But what about an accumulator? So what if we wanted to know what the value was for all the values, the sum of the values that went through the loop? So let's add another variable, and let's call that accumulator. And let's see, I don't know if we're using integers, so we're always going to end up with integers, but let's make that a real. That'll be a little bit more flexible if we decide to play around with it some more. And there's a real accumulator, and let's go ahead and set the accumulator to 0 to start with. And then let's change this and say after exiting the loop, the final value, let's say stored in the accumulator was accumulator. Okay. And let's think about this for a minute. So what is this going to produce? So it's going to have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. And you can do that math in your head, or let's run it and see if it looks like it is correct. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And stored in the accumulator is 0. What's the problem? Oh yeah, I forgot to add to the accumulator. So what we need to do here is assign the accumulator is going to be whatever was previously stored in the accumulator plus the value I. Now let's try it. There we go. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and the final value stored in the accumulator, Okay, spelling error there. The accumulator was 45. Cool. Okay, so we understand our sentry value and our accumulator and how this is equivalent to, or can be made equivalent to, the for next loop. And I think you can see it's very convenient to use the built-in features of the for next loop. The key thing to remember is whereas we have to increment or decrement a while loop that we're using as a counted loop ourselves, don't do it in the for next loop, because for next loop is going to do it for itself. And if you add this statement to adjust the index, it's going to, double increment or double decrement once that it does automatically, and once because you've done it explicitly, and that would not give you the logic that you want. Okay, so there's our example of a counted loop done both as a for next loop and using the while structure. Now let's take a moment to explore overflow conditions and overflow errors. Now an overflow error occurs when we exceed the storage capacity for a data type. So you may remember in our discussion of data types, we talked about integers, and you could store values up to a certain amount in an integer, and floating points and doubles and other kinds of data types have a maximum storage capacity because we're dealing with a finite state machine. Ultimately, we have to definitely store a value in actual memory cells, and so we have to have some number of memory cells that we devote to that number. And so that's why using the correct data type is important, because if I use, let's say, a decimal data type when an integer data type would be sufficient, then I'm actually wasting a lot of storage cells in memory for floating point values, for the decimal values that are never ever going to be anything other than 0, because integer 1 is equivalent to decimal 1.00000 repeating forever. So there has to be some limit to the storage and to the accuracy. And so I've set up a little program here that is going to continue until we forcibly exceed the storage capacity of the integer data type. And let's see what happens when that occurs. So we declare integer as I. We set I, we initialize it to a starting value of 0. And then we say, hey, as long as I is greater than or equal to 0, do the following. And to hasten things along, make our program overflow quickly, I've added 1,000,000 to I each time the program runs through the loop. Okay, so it starts at 0, it goes to 1,000,000, 2,000,000, and then what happens? What's the limit on the upper value of integer size on the system that we're using? You have to look that up depending on your computing platform, operating system, and language. In this case, it's the limit of the Flogorithm tool, whatever the Flogorithm uses for the limits on integers. If we were to convert this over to Visual Basic, it would be the upper limit for the integer type when running in VB. But let's run this and see what happens. So boom, it ran for some number of times, and it says the value was too large to be handled by your program. And it got to that when we added 1,000,000, and it got to, so it was okay at 214 billion 700 million, but when we got to 800 million, it was going to be too big, and that just didn't work. Okay, so that's the point at which the program crashed and we exceeded it. So we need to, when we're building our loops, consider illegal values being achieved not only by direct entry, but by cumulatively exceeding the data type storage capacity. So that's what happens when we hit what is technically known as an overflow condition. It's called an overflow condition because we have more digits to store, or a higher value to store in those memory cells, then we have memory cells available for that data type to store them. And so we have overflowed the capability of the storage. We've exceeded it. Let's explore another kind of special loop that is usually the result of a programming error, and this is called an indefinite or, it's called an infinite or an endless loop. And here's how an endless loop can occur. It's pretty simple and common programming error to have happen. It trips up most programmers from time to time. So here we've set up a string. We're going to call it stop loop. We've initialized it to n for no. And then we've put in the logic that says, so long, here's our test, so long as stop loop is not uppercase y and it's not lowercase y, then we're going to continue. So we're waiting for the y means stop. And meanwhile, as long as we don't have that input, we're going to output the message. Here's a random number. We're going to give them a random number up to 1 million. And we're going to add the message, isn't this annoying? And the reason for putting the random number in here is so that you can see that the screen is changing, because once it's filled the screen with the same duplicate message and is scrolling, you wouldn't actually see any change in the output of the logarithm, even though it is still adding new output. So putting this little random number in there, you're going to be able to see that things are changing. So do you see the error here? We've tested appropriately, so we have our loop structure correct, but we've never made any provision for anything to change the value of stop loop so that the Sentinel will ever be false. It will always forever be true. So let's go ahead and run that and see. And so I'm running the program and it's going and sorry Eveready Bunny, this is even going to outlast your batteries. As long as the program has power and the computer has power and it's allowed to run, it's going to run forever and ever. So yeah, probably not what we wanted. Exceptions would be is if you're programming for embedded devices and from the moment it powers up, let's say you have an intelligent, I don't know, a sprinkler timer or a steam iron or something. You want the program to run continuously as long as the device is powered up. And so you really do want an endless loop. But short of that, an endless loop, an infinite loop is usually an error. So let's also see how we would fix that error. So what we omitted was we set our logic up correctly, but there's no change so that the Sentinel value can be achieved. So the test is never going to come up with something that is going to make it false, so it will never end. If we come in here and put in a prompt to the user, do you want to stop? Enter yes or no. If they enter yes, then it's going to stop. If they enter no, then we're not. So let's run it and see if that's right. So do you want to stop? No, this is good stuff. I want to continue to do this. I love it. Oh, give me more. Ah, this is just so exciting. And finally, I get tired and say, do you want to stop? Yes, I do. Program ends. We're no longer in an endless or infinite loop situation. So notice that this is an indefinite loop, which is to say, could it run forever? Yes, provided the user continues to enter the correct entry. That do you want to stop? No. If I forever enter that, the point is not that it couldn't run forever. The point is that it is possible for it to end based on the right input, and that those inputs could logically occur. Could the user enter that they want to stop? Yes, they could. And will it stop at that point? Yes, it will. Until then, it's indefinite. The user may run it 1 time or 1 million times or 100 million times, doesn't really matter. The point is that there is a provision in the logic so that the program, the loop, can exit. If there is not that criteria, if we eliminate that, it can't possibly exit. That is an infinite loop. And again, under most criteria in most situations, that would be deemed a logic error. So don't do it. Let's explore creating a more real-world application in Visual Basic. And we'll look at this as the projected sales application. So here's our specification or our scenario. We are to create an application that displays the number of years for a company's sales to reach at least $125,000 using a 3% annual growth rate. So the application is to accept the current year's annual sales from the user, and then we'll display the number of years it will take to meet or exceed this goal. We'll look at 4 examples for solving this problem. The first will be a do while loop. A do until loop is what we will use secondly, and both the do while and the do until are pretest loops. Then we'll look at the do loop while post-test loop, and finally the do loop until post-test loop. Now let's look at a practical example of some problem solving using an indefinite loop. And we'll use 4 different examples, both pre-test and post-test. And as a checkpoint question for you, ask yourself, why are we using an indefinite loop rather than a counted loop here? And it should be fairly clear to you that this needs to be an indefinite loop. If we could count, if we knew ahead of time how many times to run the loop, we would already have our answer to the scenario. So this scenario, we're trying to calculate, given some input of current year sales, how many years at 3% growth will it take to equal or exceed $125,000 in annual sales? So I've set up our projected sales form, and I've got an enabled text box for current year sales, which the user can enter. And I've got a disabled text box because that's my shortcut. The textbook author tends to prefer using a label that they dress up to look like a text box. I find it easier just to use a disabled text box so that the program can put output to it, but the user can't change it or put input into it. So that's my preference. Either way would be fine. And that's where it's going to provide, after you press the calculate button, the result. Okay, let's take a look at our code. And so right now I have all 4 variant solutions in here. So we can do this with a do while loop. And do while loops can just be abbreviated as while loops. So you'll notice that in the description I'd parenthetically called it a do while. I've elected to save the keystrokes and just call this a while loop. And here is a do until. So both these are pre-test loops. The first 2 examples are pre-test loops. And our second 2 example are post-test loops. One using a do/loop while structure, and one while using a do/loop until structure. And probably the most important thing to notice about the difference here between while and do until: while says while this condition is true, and do until says do continue it until that condition is true. So when we're doing a comparison, those are just flip-flops. They're complements of each other. So in this one, do while sales is less than 125,000, and do until says until sales is greater than or equal to 125,000. So it's just the logical complement of that. And the same thing occurs here in the do loop while and the do loop until. In one case, the post-test condition is sales less than 125,000, and the other sales greater than or equal to 125,000. All right, before we look at the code, let's see what it does with no logic implemented, which is just our user interface. So here's our form, and you can put in some value here and hit the calculate button. And right now, I don't have that logic for the loop running, so it's not really doing too much, just outputting a 0 there. So let's go in and we'll just work down and uncomment these things one at a time. This is also a handy place to show if you have the editing toolbar turned on. There's a couple handy little buttons here: comment selected and uncomment selected. So I can take the first version except leave the line that is actually a comment line in, uncomment them. I've turned that code on, and so this will say while the sales are less than 125,000, run this calculation. update the number of years, keep looping until this is no longer true, at which point we should have the years should have incremented to the correct number of years. So let's test this and see if it seems reasonable and run it. So what would be a good test? Well, how long to reach or exceed if our first year sales are $127,000? Well, that's more than our target. So hey, you're done. Don't have to wait to grow to that. But what if I only had $5,000 in sales the first year and a 3% growth rate? It's going to take you 109 years. Not real good. How about when we're closing in on our goal? What about 124,000? You should know intuitively that 3% is going to be enough. It's going to be more than a grand, so that'll put us over. So we should see 1 year here. Sanity check. Yeah, passes the sanity check, so that looks good. Okay. All right, so that's doing the first version of the pretest loop. And let's go ahead and comment that back out. And let's test it with our second version of a pretest loop. And so let's uncomment that. And this is going to do until we reach a situation where the sales are greater than or equal to. So they've met or exceeded our $125,000 goal. The rest of the formulas are virtually identical in this case, and it will just loop until that condition has been met. So it's just one way is, stating it as a logical positive. The other one is stating as a logical negative. Let's see that they are logically equivalent. And let's see here. So if I have 127,000 in my first year, nothing to do. If I have 5,000, 109 years, and if I have 124,000, we should make it within the next year. So that's all looking good as well. So you're asking me, well, why do we need both these? Well, logically we don't. If we had a language that only allowed one, we could, anything that one can express, the other can express. It's just a question of whether we make a negative statement or a positive statement to get there. The reason it's handy that there are both in the language is that some situations are more naturally stated as positives and some as negatives. And so it allows you more clarity of thought or clarity of expression in the language. But logically, it really doesn't make any difference. But this explains why this, and also legacy support as the language has grown and expanded over the years, why we support multiple ways of creating equivalent logic. In some cases, when there are equivalent logic possibilities, one version will be more efficient than the other. In general, with respect to the do-untils and while and whiles, there's not really going to be an efficiency improvement one or the other. It's just going to be more clarity and natural expression of the problem we're trying to solve. So that's still very useful if the language gives us that flexibility. So let's go ahead and comment that back out. And now let's look at the post-test loop. So remember, post-test loop is one that runs the body of the loop first. So it's always going to run at least once. And will only run additional times if the loop at the end, or the test at the end, is satisfied. So let's uncomment that. And so this one is going to come in here and start right away, do the calculation the very first time, and it will only loop as long as the sales is less than the goal. So it's going to keep incrementing the years until we get up to our goal amount. So let's go ahead and run that. And so let's see, 127,000, we should already be there. Up 1 year. Okay, so there's something to think about in your loop logic when you're within 1 year. You got to watch out for that. So we should actually do some debugging here and say, so what is the actual number? Are our others off by 1? Let's take a look. So what if we're at 124,000 to start with? and it says we do that in 1 year. Well, that's correct. What if we're already at, what if we're at 5,000? Should be 109. Well, that's correct. So in this case, the thing we're looking at is how we would interpret that. So if we are at 127,000, it says, well, you find it within 1 year. Well, yeah, we're actually already over that. So we should change our logic if you wanted to trap for that situation. Okay, slight difference in the structure here. Okay, so let's take a look at, do we have the same issue with the other version of the post-test loop, do loop until. Okay, so let's go ahead and comment this back up and uncomment this one and run it. And what if we're already at $127,000? Yeah, and the reason is that the post-test loop, it's going to run the body of the loop before testing. Okay, so if we're going to catch that, we would need to do some other trapping here and say, well, let's compare. And if we are already at $125,000 or more, then we're just done. We don't even have to run this logic. That's why in this case, I think probably a pre-test loop makes more sense than a post-test loop, because we don't have to add the extra logic to trap that. And that's an example that will help to guide you. When is a pre-test loop, when is a post-test loop most natural, most appropriate? So I'd give an example previously, a line for buying tickets for a boardwalk attraction, the carousel. And the point being that if somebody's in the ticket line, well, they're buying at least one ticket. Otherwise, what are they doing there? Then I gave the counter example of a point in time when the boardwalk decided to consolidate their information kiosk and their ticket sales kiosk. So you stand in line whether you're buying tickets or you just have a question for the concierge. And so the concierge is now the ticket taker or ticket seller, or the ticket seller is now the concierge answering you at your questions, in which case you don't know whether the person is coming to buy tickets or not. They may have a question and not want to ride the carousel. So in that case, a pre-test loop would be more appropriate. So we sort of choose pre-test loops or post-test loops as being most appropriate to the situation. So let's go ahead and run this on the post-test do until again and see where we stand. And so again, should have the same post-test problem. I do. I'm running 1 year. And then what if I make it 5,000? Is that correct? And it is 109. What about if I'm 124,000? Do I get there? Yeah, in 1 year. So it's just that one case that we're having to look out for. And we could address that by, in the do, we could add an additional if structure and say, if sales less than 125,000, then, and we can come in and do this whole thing. So let's wrap that up inside there. And then we could come down here and say else, and we could just say, well, we know that if it's more than 125,000, then it's going to be within 0 years. So we'll just say years equals 0. And does that solve our problem? Well, let's test it. Oh, I got else if here. There we go. There we go. That should take care of it. Let's try it. And so now if I got 127,000, and now the problem is solved. Does it still work correctly for the others? Let's check. 5,000 should be 109. What about 124,000? Yeah, we're still going to solve it in 1 year. So, this solves it, but you don't, if you think about it, again, If you were using the pretest loop structure, you don't need the additional qualification of the if. So again, that's how you solve it, but I think that you can see that for the situation at hand, choosing a pretest or post-test loop as is most natural to the kind of testing you're doing, does the loop body always need to run at least once, or are there input conditions for which the loop body should not run at all, in which case use a pretest loop. And so that should give you some example and some guidance on the loops, and also give you some variations of the different loop logic that you can use. This concludes the lesson.